Okay, so this is density. Pressure, I always do a little, so this is my pressure, I always make it look like a P, and density, I always kind of make it look kind of wonky. I try to include like a little hat here, but this is density, which you should know this equation by now, right? So mass flow rate is either density times volumetric flow rate or density times cross-sectional area times velocity. So we know cross-sectional area, we know velocity, it makes more sense to use this equation. What we don't know is density. So we don't have density of air memorized. It's not on your memorized sheet. It's not given to us here. We don't know the density of air at 10 degrees Celsius. We don't even know the outcoming temperature, so we don't really know density. So in order for us to figure out density, we have a few different equations. So we know that density equals a heart, it equals mass over volume. And we also know that it equals 1 over the specific volume. Because volume, or specific volume, is just volume divided by mass. So it is the inverse of this. So specific volume is the inverse of mass over volume. And mass over volume is density. We've looked at this relationship before, but yes. So we know that density is 1 over specific volume, but unfortunately, we don't know specific volume either. So there's another equation that we can use to relate specific volume. And this is going to be our PV equals RT. I'm using specific volume because I've eliminated the mass term over here. And then when we manipulate this around to be 1 over specific volume, then we have this to be P over RT.
Wouldn't it be RT over P? She looked at, oh.
That's inverse.
Yeah, because I need this to be 1 over specific volume. So I'm going to divide both sides by specific volume and then divide both sides by RT. So now I can plug in for my density here. I can plug this in to be 1 over specific volume times cross-sectional area times velocity. And then I can plug in my 1 over specific volume to be P over RT times cross-sectional area times velocity. And now I know pressure, and I know my R value I was given. My temperature, I'm given at 0.1. My cross-sectional area I'm given, and my velocity I'm given for 0.1. So for this point over here. But if I solve for my mass flow rate at 0.1, well, it's the same as my mass flow rate at 0.2. So it doesn't matter if here I'm solving for pressure at 0.1, temperature at 0.1, velocity at 0.1, if I'm solving for my mass flow rate at 0.1, because it's the same mass flow rate. We have a conservation of mass flow rate that's happening here. So it's okay for us to solve for mass flow rate at 0.1, even though technically it's asking for mass flow rate at 0.2 or just a general mass flow rate. All right, so now when I plug this in, I have my mass flow rate is going to be equal to pressure over RT times cross-sectional area times velocity, which is, I think I wrote 800 kilopascal. It's 80 in the problem statement, I believe. Somebody double check me, right?
That's it.
It's 80. Okay, got carried away. All right, so we have 80 kilopascal divided by our R value, which was given as 0.287 kilojoules per kilogram Kelvin, times our temperature, which we want to get into Kelvin here. So 10 degrees Celsius plus 273 Kelvin. This is going to be multiplied by our cross-sectional area of 0.4 square meters, and then our velocity of 200 meters per second. So we're going to have Kelvin that cancels, and we're going to have cubic meters per second kilopascal divided by kilojoules Kelvin. And we can remember that if we, so conversion is here.
How is it the kPa times m cubic?
Yeah, I think it's 1 kilopascal cubic meter is 1 kilojoule, right? Would that work for us? Kilopascal cubic meter kilojoule, which leaves us with kilograms per second. Yeah, so we need to do this conversion from kilopascal cubic meter to kilojoule. So then kilopascal cubic meter, those are canceled, kilojoules were canceled, we'd be left with kilojoules per second. So working this out, we get 78.8 kilograms per second as our mass flow rate of our air in the diffuser. Are there any questions about that? As a note to the people online, I don't think I'm hearing sound from online very well, so definitely try to use the chat, please. All right, so that's part A, our mass flow rate of air in the diffuser. For part B, we're going to use our energy equation. So for part B, we're asked to find our temperature here. So we now know our mass flow rate is 78.8 kilograms per second. We're trying to figure out the temperature at the end of this diffuser. So do you, okay, yeah, I'm not gonna ask that. All right, so for part B, we're asked to find temperature coming out of the diffuser, so T2. So one of the things that we still need to hold true is mass flow rate at point 2 is equal to our mass flow rate at point 1 is equal to our mass flow rate. This is because we are a single stream, steady flow system. So we also are going to go to our energy equation now, which is this Q in plus work in plus the summation of our mass coming in is equal to our Q out plus our work over time out, or power out, plus our summation of our outgoing mass energy. So this is our main energy equation for this chapter. We're told in that little schematic on the side, I'm not going to stop share because it's hard to get the Elma back up, but we're told in the little schematic on the side that here we have an adiabatic. We have an adiabatic diffuser, which means we're not losing heat, really. It's not really about this heat transfer, this Q term. That's not something we're concerned about. That's in the problem statement as adiabatic. We also don't have any power that's being done. This diffuser is happening just because the air is coming in at a certain velocity. We don't have any shaft that's being done, like with a turbine or anything. And then we don't have any height difference. So our Z at point 1 is equal to our Z at point 2. So essentially there's no height change. There's no difference in height that's happening. So therefore our heat and work are negligible. And when we look at our mass flow rate equations, here's where we have our mass flow rate of 1. 1 is our coming in flow rate. So our mass flow rate of 1, our change in kinetic energy, plus our change in potential energy, plus our change in internal energy, plus our pressure times our velocity, volume, specific volume.
Almost there.
You take your time, you're doing really good.
And this is going to be equal to our outgoing mass flow rate plus our outgoing energy, specific kinetic energy, potential energy, internal energy, plus our pressure times our volume term. Running out of room there, but oh well. So remember that this combines into enthalpy. This is the definition of enthalpy. So this will be enthalpy at 0.1, enthalpy at 0.2. And we don't have any potential energy because we don't have a height change. So therefore, our equation reduces down to our mass flow rate at 0.1 times our change in kinetic energy plus our enthalpy value at 0.1 is equal to our mass flow rate at 0.2 times our change in kinetic energy plus our enthalpy value at 0.2. We know that our kinetic energy value is 1/2 velocity squared. So 1/2 velocity squared plus h1 is equal to m2, 1/2 velocity squared plus h2. These are going to be velocity at 0.2 and 0.1. Remember that M1 and M2 are the same value. So if we move this unit to this side, we therefore have 0 is equal to 1/2 velocity at 0.2 squared plus h2 minus 1/2 velocity at 0.1 squared minus h1.
Velocity change is negative.
Yeah, so velocity 2 is negligible, which I will do in just a second. Sorry, I'm looking at the solution and this is what they have as the next step, but I'm,
Confused about the units. How would they put units in there? Would be like the velocity squared over 2 would just be like meters squared per second squared.
well, where's this mass, where did this mass term go? Why is it not here?
Well, if they're the same on both sides, I guess they just drop it.
Okay,
But I don't know, it's still confusing because the units, I got to that point too,
yeah,
and I got stuck because I was like, the units don't really make a ton of sense.
yeah. Well, I have a conversion for the units that we can use. So for this problem, we're looking for the temperature change, which we're going to look up in the property table based on our new enthalpy value. So what we're trying to get is we're trying to solve for our enthalpy value at 0.2. So I think since the mass flow rate units are the same, it kind of becomes not important here. They factor it out and then they kind of just drop it. I don't really like that solution, but I'm gonna keep going. So like I said, we're trying to figure out temperature based on this enthalpy at 0.2. We can go to the property table, see what our corresponding temperature is based on this enthalpy value here. So if we do our enthalpy value at 0.2, we move it over to this side, then we have our, so this would become negative, so I'm gonna switch everything from negative to positive, right? So negative 1/2 velocity at 0.2 squared plus 1/2 velocity at 0.1 squared plus h1. We know this velocity at 0.2 is pretty much 0. And we can look up our enthalpy from a property table, and we know the velocity at this point. So therefore, we get 1/2 200 meters per second squared, plus, we're gonna get our enthalpy term from the back of the book. So our enthalpy at 0.1 is at, we're gonna go to table A17.
Why didn't it interpolate, but it was like just above 370.67.
You got it to be what?
Well, if you want to be like really accurate with the interpolation, but there's no 373 to the temperature that we were at.
Okay,
But I just used 370, and it was 370.67 kilojoules per kilogram for HM.
okay. Wait, so what did you look up to be your enthalpy?
I just did the interpolation. So table A17, I used the temperature at 373 that we had, and it was between 380.77 and 370.67. I get 373.7 kilojoules per kilogram.
Okay. So in this solution that I have, it's saying this enthalpy is 283 kilojoules per kilogram. But oh, okay, I get it.
10 degrees, would it be the temperature or the pressure table?
Well, they have for the ideal gases, they have it based off the temperature.
Yeah,
I have 2,519 for H.
okay, well, so here, okay, I figured out the issue. So we're looking at ideal gas properties of air. It's table A17 in the 8th edition, it's A21 in the 3rd edition from 2008. And then if we look at, we have an incoming temperature of 10 degrees Celsius, which is 283 degrees. So we're gonna be a little bit above here. So we're gonna be between 280 and 285. So it's okay to approximate as 283.
Yeah, I'm sorry, I don't know why I said 373.
You're
I meant 283.
You're fine, no, that's good. It's good to like question it, right? Because then I just kind of blindly trust the solution sometimes. So keep in mind, this is not saturated water, this is not refrigerant, this is a ideal gas property of air. So this is the first time we've looked up enthalpy for an ideal gas. So we can go to this table, look up our temperature in Kelvin. We're at 10 degrees Celsius, which puts us about right here. So we're at about 283 kilojoules per kilogram as our H1 of our incoming stream. So 283 kilojoules per kilogram. And then as was mentioned, these units don't really seem to be matching. So what we did in terms of a conversion was we did 1/2 200 meters per second squared times this conversion. 1 kilojoule per kilogram is 1,000 meters squared per second squared. plus 283 kilojoules per kilogram. So when we add these together, so 200 squared divided by 2 divided by 1,000 plus 283, we get this to be 303 kilojoules per kilogram as our H2 at our outlet. Can't go any higher. So therefore, we can go back to table, the ideal gas air table. And we can figure out what temperature this corresponds to. So if I go back to table A21 or A17, whatever it is in your book, and I look for my enthalpy value of 303, I'm gonna be right between these two. I'm gonna be about 303 degrees Kelvin. So the answer, 303 degrees Kelvin, which is roughly like 30 degrees Celsius. 30 degrees Celsius. So that's our temperature at T2. So I don't expect you to memorize this. I would give you this on an exam if you need it. Are there any questions about this problem? All right. So the solution is posted, and let's start on problem number 2. All right, so now let's work on, yeah, sorry, no, I didn't see that in the chat. When we're looking at a diffuser, thanks for answering, Justin. But when we're looking at a diffuser, the purpose of a diffuser, remember the example with like a blow dryer in your hair? The purpose of a diffuser is, oh, okay, you got it. Yeah, it's assumed to be so much lower that it's 0. So whatever's coming out of this diffuser is so much lower than what's coming in that we say is negligible. Yep, so glad you figured it out. Thanks for asking a question. And let's go back to number 2 then. So let's work on this for a couple minutes and I'll go over it. It's already 12:30, so maybe like 7 minutes and then I'll start going over it. So number 2 has this corresponding schematic. So you want to look at your Cody, right? And then you hear my announcement about this place. Okay, so the exam average is much lower than I hoped it would be. So I am offering a quiz to get extra points next Friday in class. So March 26th during this time period. It'll be 2 questions about an hour, and whatever points you earn on the quiz will go back to your exam. So I'm thinking it's going to be a maximum of like 20-25 points, and it'll be added directly to your exam. It can't hurt you in any way. So if you get a 0, your exam grade stays the same. You won't drop in points at all. Okay. The like, oh yeah, I just printed it for you. Yeah. So grab it from the printer.
So would this be a pipe deductible?
Oh yeah, I didn't realize I printed. Okay, thank you.
Should it? It's going on, right, so,
What's the question? Jeannie?
oh, I thought it would be a pipe deductible.
It does look like, if this wasn't here, it would be pipe duct, but since you have the throttling valve, it's still on top. And remember, the throttling valve is determined by a big drop in pressure, which is why we're not gonna turn the UPV into enthalpy. We're gonna leave them somewhere. This pressure is a big deal. So yeah, questions so far? Oh. Yeah, I should print some copies and bring them on Friday, so maybe I'll do that. Great. Yeah.
It's okay.
Yeah. All right, it might have not been helpful what I told you. You can keep working with Infobate. So looking at the description, we do just keep working with Infobate. It's okay to. Sorry, that was confusing.
It's like the other questions that we have, and those that are given values like the internal energy.
So, this is like a little cheat. These are telling you what like you should look up for your tables, yeah. So this is kind of giving you the answers there if you don't already have the tables. They're not super easy to see, but that's internal energy, PV, and H. So it is, they already looked it up in the property tables and like gave you those values here. So you don't even have to look it up in the tables, which is nice. I'll move the chat so you can see it. All right, so I'm gonna go over it in like another 2 minutes. Sorry, it's kind of fast. Time to work on it. All right, so I'm gonna already go ahead and go over it. I'm sorry, it's not that much time, but I don't wanna like run out of time. So maybe if you one more time, work on it yourself later, see if you can redo it without looking at the solution. Especially, we're still kind of new at doing these, so hopefully it's not a problem. All right, so we are looking at expansion of refrigerant R134A in a refrigerator. And we have a refrigerant R134A coming in at 800 kilopascal as a saturated liquid. So here's a clue. We have saturated liquid vapor table, and it's leaving at 120 kilopascal. We want to determine the quality at the final state. Here's another clue. We're still saturated liquid as well as the temperature drop. So we know what table we need to use and we know pressure at both 0.1 and 0.2. So when we're looking at our throttling valve, we have some sort of, duct type thing. We have our throttling valve in the middle that is causing a pressure drop in our refrigerant. On one side, we're flowing through here. We have 0.1 on this side, 0.2 on this side. We're coming in at 0.8 megapascal, and we're leaving at 0.12 megapascal. And we know that we are a saturated liquid vapor of R134A, which means tables A11, A12, A13. I think it's just A11 and A12 for saturated liquid vapor. So we want to first determine the quality at our outlet. So what is the quality over here? We know that we're coming in as a saturated liquid. So over here, we know that we're a totally saturated liquid. Over here, we know we're a saturated liquid vapor because there's a quality term. So when we go to our table A12, we can go to table A12, which is our saturated liquid vapor for a R134A refrigerant. When we go to this table, we can see that at our pressure is 0.8 megapascal. We are a saturated liquid, meaning we are only this sub F subscript. When we go to table A12, we can see that our temperature is going to be our saturation temperature at 0.8 megapascal, which is 31.31 degrees Celsius. I'm using an old edition of the book. It might be slightly different for your newer edition. It might be like 31.37 or something. That's okay. And our enthalpy at 0.1 is going to be our enthalpy sub F at 0.8 megapascal, which is 95.47 kilojoules per kilogram. These are from table A12. Then, so this is for 0.1. We know at 0.2, we're going to be a mixture. So we're not a saturated liquid. We still have our pressure is, so this is P1, this is P2, if that helps at all. Our pressure is 0.12 megapascal, and we are a mixture. But one of the things about throttling valves have a big pressure drop, but they have roughly equivalent enthalpy values throughout this system. So the heat content of our system is not really changing. That's not why we use throttling valves. We use throttling valves to change the, to have a huge pressure drop. But one of the rules of throttling valves is this enthalpy is roughly equal. So that was given to you in the schematic. I also highly encourage you to do some readings because there are these kind of assumptions that we make about different engineering devices that take too long to go through individually. So please do yourself a favor, do your reading, make sure that you're understanding these different devices. So we also have this consideration that H2 has to be roughly equal to H1. So when we look at our property table, table A12 again, we can see that our H sub F at 0.12 megapascal is equal to 22.49 kilojoules per kilogram. And our H sub G at 0.12 megapascals is equal to 236.97 kilojoules per kilogram. Once again, I'm working with an older edition of the book because I leave my book different places. So if your values are slightly different, that's okay. If you're like, oh, mine's 237.3 or whatever, that's fine. It's just different editions of the book. So we know that our H2 has to equal our H1, which is 95.47 kilojoules per kilogram, at least roughly, which puts us in the middle here, which we already know because we're asked to find quality. But we can see that we're not gonna be a very low quality, we're not gonna be a very high quality. We're gonna be, kind of somewhere in the middle, maybe like 3/4 of the way. So somewhere 0.2, 0.3, 0.4, that's what I'm gonna estimate our quality to be. But I know that my quality equation, one of my quality equations is you should all be familiar with this now, my enthalpy value at the point I'm interested in, minus my enthalpy value of my saturated liquid, divided by my enthalpy value of my saturated liquid vapor. So I have everything that I need to solve for enthalpy now, right? I have all of these values that I need. So this is 95.47 kilojoules per kilogram minus 22.49 kilojoules per kilogram divided by the difference between my saturated vapor and my saturated liquid. So 236.97 kilojoules per kilogram minus 22.49 kilojoules per kilogram. All of my units are going to cancel because they're the exact same units. Quality is a unitless property, so that looks good for us. And when we work this out, it is 0.34 as our value for quality, which makes sense logically looking at our placement between our saturated liquid and our saturated vapor values, right? It's about maybe 1/3 of the way there. Okay, sounds good. So that's part A. I'm gonna quickly go through part B because now we're at the very end, which is to look at the temperature drop. So for part B, we're trying to look at the temperature drop that's occurring. And the way that we're doing this, we have our change in temperature is T2 minus T1, pretty simple. So we know our T1, right? So we know T1 is our saturation temperature, our Tsat of 31.31 degrees Celsius. Our T2, we don't really know, but when we think about it, all right, so we know that our leaving refrigerant is still a saturated liquid vapor. It's a mixture, which means that that entire mixture is at our saturation temperature. So we need to find the saturation temperature. So this is Tsat at 0.8 megapascal. We need to find our Tsat at 0.12 megapascal, which our Tsat at 0.12 megapascal is 22.32 degrees Celsius negative. Sorry, negative 22.32 degrees Celsius. And this is made easy because we are told that it's a saturated liquid and then we're told that it's a mixture. So we're only ever using table A12. All right, so then our temperature equation just becomes negative 22.32 degrees Celsius minus 31.31 degrees Celsius is equal to minus 53.63 degrees Celsius.
What was the final answer for number, or for part A again?
So the final answer for part A is 0.34 is our quality. So we're about 1/3 of a total mass is our vapor. And then for part B, we're at a very cold temperature. So that makes sense because this is a refrigeration unit. We're trying to go from roughly room temperature, a little bit cooler, to very cold. So this is very, very cold actually. This is an expensive freezer. All right, so with that, I am done with these problems. These solutions are posted on Canvas, and please, let me know if you have any questions or concerns over email. Otherwise, have a great weekend. I will see you all next week.
Have a good weekend.